So today we'll be going over first order linear differential equations and how to solve them. Now, previously we learned how to solve differential equations by the separation of variables. So we get a differential equation like of this form, for example, dy dx plus 2xy squared is equal to 0. Now, this particular case, you were able to actually separate the variables, the x from the y, so you have the y on this side and the x on the other side, and from here all you have to do is integrate both sides and solve this differential equation. Pretty straightforward. Now, what if you actually come up with a differential equation that you're not able to separate the variables, the x's from the y's, and so that would we would utilize a different method to solve this differential equations, which we'll be going over in this video. Now, keep in mind this method can also be utilized in differential equations where you could still in fact separate the variables, so it could be used in either or cases. So let's go ahead and see our first example. So for our first example, we have 3 dy dx plus 12y is equal to 4. Now there is a standard form to start solving these differential equations, which is of the form dy dx plus some function times y is equal to g of x. Now this is your standard form to start utilizing this method. So as you can see, our first example, we need to get rid of this 3 coefficient of dy dx. So all we do is divide both sides by 3. So once you divide both sides by 3, you have dy dx plus 12 over 3. Y is equal to 4/3. Of course, this is equal to 4 here. So now we have it in this standard form, right? We have our p of x in this case will be the 4, and our g of x will be 4/3. Now for the first step here, we integrate our p of x dx. In this case, it'll be just 4. Keep in mind it's being multiplied by y, but our p of x in this case would just be 4. So the integral of 4 is equal to 4x here. And from here, we just add a base e. So this is your integral of p of x dx. Your base is going to be e. So e to the 4x, right? So just for some clarification, this is our e to the power of the integral of p of x dx. So this is our first step, right? So we got the integral of px dx is equal to 4x and base e, so it's e to the power of that 4x. And from here, now we multiply both sides of the equation with this e to the 4x. After that, we have e to the 4x times dy dx plus 4 times e to the 4x times y is equal to 4/3 e to the 4x. Now, another way of writing this is saying the derivative of x of e to the power of 4x times y is equal to your right hand side of the equation. Now, why exactly is that? Now, you could go ahead and just apply the chain rule to this side of the equation, and you will see that you will get the equivalent to what you see beforehand here. So just applying the chain rule is the derivative e to the 4x times y plus the derivative of y times e to the 4x. You will in fact get the above equation. So it's in fact equivalent, saying these two, it says the same thing essentially, right? So from here, all you have to do is integrate both sides of the equation. Of course, the integral of a derivative, that basically just cancels out, and you're left with, on the left-hand side, e to the power 4x times y is equal to e to the 4x divided by 3 plus an arbitrary constant. Now you divide both sides of the equation by e to the 4x, and you get y is equal to 1/3 plus the arbitrary constant c times e to the negative 4x, and this is your solution to the differential equation. Now keep in mind I'm going over examples utilizing this method, but I did not prove this method, so just keep that in mind throughout this video. So I left the general form of the linear first order differential equation here just for reference. And for this next example, we have x squared times y prime plus xy is equal to 1. So now first let's go ahead and get it to the standard form we see above. So just divide both sides of the equation by x squared, you get y prime plus 1 divided by x times y is equal to 1 over x squared. So in this case, our e to the power of the integral of p x dx is equal to equals e to the power of ln of x, which is equal to x, right? Your ln is base e, and you have base e. They both cancel out, and you're left with x. So now you go ahead and multiply both sides of the differential equation with this value. And you have x, y prime plus y is equal to 1 over x. And this is equivalent to saying the derivative of x, the derivative with respect to x of x times y, you applying the chain rule is x y prime plus derivative of x plus times y. So it's equivalent to saying this, and now you just integrate both sides and solve. So on this side, basically your integral and the derivative cancels out, and you're left on the left-hand side, x times y is equal to ln of x plus the arbitrary constant. You get it to your standard form, leaving y by itself on one of the side of the equation. And this is your general solution to the differential equation. Y is equal to ln of x divided by x plus 1 over x times your arbitrary constant c. So for our next example, we have L didt plus Ri is equal to E. And we see that we have initial condition. At 0, we have the function I is equal to I naught. Now this is maybe a little bit more different than from what you're used to seeing with the variables x and y, but you apply the method the same as you would. So let's go ahead and get it to the standard form. So you divide both sides of the equation by L, and you see that your P of x is R divided by L. So we have e to the power of the integral of R divided by L with respect to t, and that is equal to e. Since R are constant, so it's RL times t. And now you multiply both sides of the equation by this, and you get e to the power r over L times t didt plus the same base e r over L times I is equal to e over L times e to the power rt over L. Now from here is the same as saying the derivative with respect to, in this case, it's t, not x, right? With respect to t of e to the power rt over L times I is equal to e over L times e to the power RT over L. So now in this case, we go ahead and integrate both sides and we solve. So after making some simplifications, we get I to one side of the equation by itself. I is equal to E divided by R plus your arbitrary constant times E to the power of negative RT over L. Now in this case, this is your general solution, but keep in mind, we do have this initial condition, so we're able to solve for the arbitrary condition. So let's go ahead and do that. So our initial condition when t is equal to 0, your function is equal to I naught. So let's plug in 0 for t and solve for c. So whenever you have anything to a power of 0, it automatically equals 1. So you have e over r plus your arbitrary constant is equal to I naught, and your c is equal to I naught take away e to r. So now let's go ahead and plug it into a general solution. And so this is the solution to the differential equation. So this is how you solve first order linear differential equations. Now I would like to reiterate, the other method is by separation of variables. Usually when you're able to have your x on one side of the equation and your y's on the other side, but keep in mind this method can be used for that situation as well. But sometimes when you can't separate the variables, you will have to use this method. Now, if you're interested in looking at the proof of how this method works, then you could go ahead and reference your differential equations textbook and such.